In this video, we're going to be reviewing torque and rotational motion. To rotate a wrench like the one you see here, the most effective way would be to push on it in a perpendicular direction. To calculate the torque, we would take this r, this radius vector, times the force that you're pushing in the perpendicular direction. So I'm just going to put a little perpendicular symbol right here. So if the force and the radius vector are perpendicular, this is the equation that you would use. The symbol for torque is this Greek letter tau, and if we have a situation where the force was in the direction of the radius vector, so maybe it's being pulled away or towards the axis of rotation, then the torque would be 0. Now, what if you're pushing on it at an angle, so such as this one right here? Then what we want to look at is the perpendicular component of the force, and that would be this component right here. And so what we're really interested in is the perpendicular component. And if it is at an angle, there's a couple ways we can solve this. One is to calculate RF sine theta, and the other way is to use what's called the lever arm. So the lever arm is a straight line perpendicular to the line of action, which is this force along this force vector here, and that goes through the axis of rotation. So this line right here is called the lever arm. So that is another way to calculate torque. So torque, another way, is to take the lever arm times the force. One way that we can think about torque is that it is like a twisting force. However, we want to be careful that it is not a force, because forces are measured in newtons. However, torque is measured in Newton meters. If the net torque on a system is 0, then we say that the system is in rotational equilibrium. By that, what we mean is that an object, if it's not rotating, it's not going to start to rotate. And if it's already rotate, it's going to continue rotating until there's a net torque acting on the system. So here's an example of rotational equilibrium. So we have a seesaw. On the right hand side, we have a mass M. So the force acting on this mass, the force of gravity, is mg. On the left hand side, we have a mass of 2m. So the force of gravity there is going to be 2mg. And the distance from the mass to the axis rotation on the left is r. And the distance of the mass to the axis rotation, we're going to say that's 2r. So if this is a rotational equilibrium, what we do know is that the torque on the left is equal to the torque on the right. The torque on the left causing it to rotate counterclockwise, and the torque on the right causing it to rotate clockwise. And the torque on the left is going to be r times the force perpendicular, which is 2mg. And then on the right hand side, the torque is going to be r times the force perpendicular, so that the distance is 2r, and then the force is going to be mg. So we can see that on both sides we have 2rmg, and then on the right hand side 2rmg, and so we know that this seesaw right here is in rotational equilibrium. Now we're going to compare kinematic equations for linear versus rotational or angular motion. So we'll start with the equation for constant velocity. Now you could use this equation for average velocity as well. Either way, the rotational version of this equation is going to be angular velocity, which is equal to the angular displacement, which is delta theta, the Greek letter theta, divided by the delta time. Okay, so that defines kind of what angular velocity is, which is going to be the change in the angle divided by the change in time. If the angular velocity is not constant, this will give you the average angular velocity. Next, we'll look at delta x equals vit plus 1 over 2 at squared. The rotational version of this is the angular displacement. So anytime you see displacement on the linear equation, you're going to substitute that with angular displacement for rotational motion, is equal to the angular velocity initial times t plus 1 over 2, and the rotational version of acceleration is angular acceleration. We use the Greek letter alpha, and times the time squared. For Vf equals Vi plus At, it's going to be the angular velocity final, and the Greek letter here is omega. So omega final is equal to omega initial plus alpha t, and alpha once again is angular acceleration. For vf squared equals vi squared plus 2a delta x, this is a good equation if you don't know the time and you're not looking for the time. So if that's the situation, always consider using this equation. So this is going to be the angular velocity final squared is equal to the angular velocity initial squared plus 2 times the angular acceleration times the angular displacement. And lastly, we have delta x equals 1 over 2 times vi plus vf times t. So basically, this equation is kind of like the equation above. It's kind of like this equation, delta x equals vt. It's kind of like writing like that, except here we're using the average velocity. The average velocity is, for a constant acceleration problem, is 1/2 times the initial velocity plus the final velocity. The rotational version of this would be the angular displacement is equal to 1 over 2 the omega initial plus omega final times the time. So now we're going to look at the relationship between linear and angular quantities. Here I have a circle. We're going to cut out a little slice of it. And we have a arc length of s, and we also have a central angle theta. And basically it just means that the legs of this angle crosses the ends of the arc length. So if I take theta and set that over the arc length, I can use a proportional reasoning here and say that the complete circle, if we were to go all the way around the circle, which is 360 degrees, except we're using radians, we're going to say 2 pi. The circumference, the distance that you're going to cover going all the way around, is going to be 2 pi r. So here we're using proportional reasoning. The central angle divided by the arc length is equal to 2 pi rad going all the way around that angle divided by the circumference of the circle, because that's the distance when you go all the way around a circle. You'll notice that the 2 pi's cancel out and we get that theta is equal to s over r. So the angle in radians is equal to the arc length divided by r. We can also rewrite this as theta r, so we're taking the angular quantity times r, and that gives us a linear quantity, which is s, the arc length. And this could be very helpful when you're going from linear to angular or angular to linear. Now let's take a look at angular velocity. So let's say that this is a circular disk and it is rotating, and there's a certain location here, and at this location, maybe this is a merry-go-round, and so let's say you're on a little horse here, and at this location as it's rotating, you're going to be moving in this direction. You're going to have a certain velocity, and you're also going to be at a certain distance from the axis of rotation. Now I want you to think about this. So your angular velocity as you're going around is going to be the same. It doesn't matter where on the platform you are, you're going to have the same angular rotation, because it's just the theta, the change in theta divided by the change in time. And that is equal to v over r, v over r. So one way to think about this is that if you were farther away, let's say you were over here, okay, and you were on a horse over here, you're going to be going faster. And the reason for that is because you're going to be going through a bigger circle, right? So the v on the right here is going to be going around at a bigger circle, so you're going faster. The little v, you're going around a smaller circle in the same amount of time, so you're going to have a smaller velocity. So I can rewrite this equation as omega r is equal to v. And hopefully this makes sense, because the farther you are, the bigger the r, the faster you're going to be going, the greater the velocity. So this is another helpful equation right here, just to connect your angular quantity, the angular velocity, connected to your linear velocity. And then the third circle here, I like to consider acceleration. So let's say that this is rotating and it is accelerating. So it has a certain amount of angular acceleration. So for example, maybe a DVD in a DVD player, when you start up, it's going to start to rotate faster and faster. And let's consider a point here on the edge of this disk here. There's going to be two different accelerations. And so I just want to take a moment to clarify that. So you're going to have one which is the centripetal acceleration, and just to remind you that centripetal acceleration is equal to v squared divided by r. And there's also going to be a tangential acceleration. And this tangential acceleration is equal to the angular acceleration. So angular acceleration is equal to the tangential acceleration divided by r. And we can rewrite this as alpha times r equals to the tangential acceleration. Now there's also a velocity, obviously, at this point right here, but I'm focusing on just the acceleration. So I'd like you to take a look at all three of these equations, this one, and this one, and notice how to go from the angular to the linear quantity, we take the angular quantity times r, and that equals the linear quantity. And with the acceleration, be careful that there's two accelerations there, because we also have centripetal acceleration. If it's going in a circle or in a curved path, it's going to also have an angular, it's also going to have a centripetal acceleration. So now we're going to compare graphs for linear versus rotational motion. In linear motion, the slope of a position versus time graph represents the velocity. On a angle versus time graph for rotational motion, the slope represents the angular velocity. For a velocity versus time graph linear motion, the slope represents the acceleration. For rotational motion, angular velocity versus time graph, the slope represents the angular acceleration. So by understanding linear motion and how to graph it and what the parts of the graph represents, it really helps you to understand rotational motion. Also, the area under the curve for a velocity versus time graph, this area right here represents the change in position or the displacement. And for a angular velocity versus time graph, the area under the curve here represents the change in angular displacement. So once again, if you have a solid understanding of linear motion, it's super helpful to understand rotational motion. So now we're going to compare dynamics for linear motion versus rotational motion. We know that acceleration is equal to the net force divided by the mass. This is Newton's second law. The rotational version of this is that angular acceleration is equal to the net torque on the system divided by what we call the rotational inertia or the moment of inertia. We'll say more about that in a moment. So let's take a look at what this is telling us. This is telling us that there will be an acceleration linearly if there's a net force on the system. And that acceleration will also be affected by the amount of mass. We can also rewrite this as F net equals ma. In other words, if you apply a net force on a system, you will cause that object to accelerate. Now, the rotational version is telling us that it's going to rotate angularly, and it's going to have an angular acceleration if there is a net torque. So if there's no net torque, the angular velocity will be constant. If there is a net torque, the angular velocity will change. It also is affected by the rotational inertia. I think of this as resistance to a change in rotational motion or a sluggishness in wanting to change its rotational motion. We can write this as the net torque is equal to I times alpha. Just another way to think about it, that if you have a net torque on your system, you will cause it to have an angular acceleration. Its rotational velocity will change. So if you have a net force, then there will be an acceleration. And if you have a net torque, you will have an angular acceleration. Now we're going to take a closer look at the moment of inertia. So the moment of inertia is an object's resistance to a change in rotational motion. And the equation is I is equal to 1 over 2 mr squared. And sometimes we'll call this a moment of inertia, and sometimes we'll call this rotational inertia. So here we have two rods below. One rod, two masses that are at a certain distance. The second rod has masses that are a little bit closer. So the one on the top would have a greater moment of inertia because the r is going to be bigger, and the one on the bottom will have a smaller moment of inertia because r is closer. What this is telling us is the one on the top is going to be harder to get it to rotate if it wasn't moving, and the one on the bottom is going to be easier to get to rotate if it wasn't moving initially. Now let's compare a disk and a hoop. So this hoop has its mass concentrated farther away from the axis of rotation. So let's say this is the axis of rotation. And while the disk, this one's the disk, its masses are concentrated at different radiuses from the axis of rotation. And they have the same total mass. So now let's compare the moment of inertia or the rotational inertia for a disk and a hoop. So what you'll notice between these two is that for the hoop, the mass is concentrated farther away from the axis of rotation, while the disk has mass that's kind of spread out throughout its axis rotation. It's at various distances. And so the moment of inertia for the hoop is going to be greater than the moment of inertia for the disk. And I want to make sure that you understand why. The reason is because even though they have the same mass, the distribution of the mass, where is the mass, makes a difference. And the mass for the hoop, they're all at a distance of r, while the mass for the disk, some of them are at r distance and some of them are closer. And so the moment of inertia for the hoop, it will be greater than the disk. What this means is that to get the hoop to rotate, it's going to be more difficult than getting the disk to rotate. This chart on the right is helpful when you're dealing with objects that have more than one particle. And so rather than adding all the 1 over 2 mr squares, we can use this chart, and it's a little shortcut and allows us to compare the moment of inertia or the rotational inertia for different objects such as a sphere or a cylinder or a hoop. Now we're going to look at the rotational version of the work energy theorem, and we're going to derive kinetic energy for rotational motion. We know that the net work is equal to the net force times displacement. I'm going to multiply R to the F net. This will give me torque, and I'm also going to divide R to the displacement. And this way the R's, I'm not changing the right-hand value overall. So then the net work is going to be equal to the torque, and remember that S over R is equal to theta. We were relating rotational to linear quantities, and this was one of them. So I can substitute delta theta, or the angular displacement. And we also know from Newton's second law, the rotational version of Newton's second law tells us that the torque is equal to the moment of inertia times the angular acceleration. So I'm going to also make this substitution right here. So we have I alpha times the angular displacement. And then I'm going to use a kinematic equation for rotation. So I'm going to substitute the angular acceleration times the angular displacement into my equation. And that gives me the net work is equal to 1 over 2 I omega final squared minus 1 over 2 I omega initial squared. And this 1 over 2 I omega squared is what we call the kinetic energy for rotation. So rotational kinetic energy is equal to 1 over 2 times the moment of inertia times the angular velocity squared. So now we're going to apply the conservation of mechanical energy to a rotation problem. So here we have a ball that's rolling down a ramp. Initially, it has a certain amount of gravitational potential energy. I'm going to go ahead and create a bar graph down here. So let's say it's got 3 amounts of boxes and it has a certain amount of mass. So initially, it's got mgh. Okay, and let's say initially it's not rotating, it hasn't, doesn't have any, initially isn't moving, so there's no translational kinetic energy and no rotational kinetic energy. And then it starts to roll down. Not only is it moving linearly down, it's also rotating. And so once it gets to the bottom of the ramp, it has no more gravitational potential energy. However, it will have converted some of that to translational kinetic energy, and some of that will also be converted into rotational energy. And so as the ball rolls down the ramp, there's a change in the form of energy here from gravitational potential energy, energy stored in the gravitational field, and now it's converted to the energy of motion stored in the motion of the object. And the equation for translational kinetic energy is 1 over 2 mv squared. The equation for rotational kinetic energy is 1 over 2 I omega squared. And the I is rotational inertia. Omega is the rotational velocity. Now we're going to compare angular momentum to linear momentum. And it's helpful to remember that if the net torque is 0, then the angular momentum is going to be conserved. So let's go ahead and start with linear, which is linear momentum is equal to the mass times the velocity of the object. The rotational version of it is the angular momentum, which has the symbol L, is equal to the rotational inertia, or the moment of inertia, I, times omega, the angular or the rotational velocity. We also have the impulse momentum theorem, which is F delta t, the impulse, is equal to the change in momentum, delta p. The rotational version would be torque times delta t is equal to the change in rotational or angular momentum. Now, if we have a net force of 0, then we know that the final momentum is going to equal to the initial momentum. And for rotational motion, if the net torque is 0, then we can say that the final angular momentum is equal to the initial angular momentum. So now we're going to take a look at an application of the conservation of angular momentum for an ice skater. So on the left, the ice skater is stretching their arms out real far and their legs are stretched out as well. And so this ice skater has a certain amount of angular velocity, omega. And then as this skater brings their arms in, you'll notice that the skater is going to start to rotate faster, and I'll represent that with a larger symbol of omega. So let's think about what's going on here. So initially, the skater has a certain amount of moment of inertia, which the symbol for that is I. And then when they bring their arms in and their legs in, now they've moved the location of the mass closer to the axis of rotation. And so they're going to have a smaller moment of inertia. And as a result of that, the skater's angular velocity is going to increase. So it's going to have a greater angular velocity. However, the angular momentum initially is equal to the angular momentum after the arms are pulled back in. So the angular momentum is conserved because there's no external net torque. And if there's no external net torque, the initial angular momentum will equal the final angular momentum. So now I'd like to show you how we can set up a disk collides with a rod problem. So here we have a rod, it's on a table, it's on a flat surface table, and it's frictionless table. It's got an axis of rotation at the bottom here, and the ball is coming and hitting this rod. So we have the before and we have the after situation here. So assuming that there are no external net force on the system along the kind of the plane of the table here, we can say that the initial momentum is equal to the final momentum. And the initial momentum is going to be I omega of the ball, and then after it collides, we're going to say it's going to stick to the rod, and so the rod ball is going to have a momentum of I prime times omega prime. And now we're going to calculate the moment of inertia of the ball, which is going to be r squared, and omega, remember we can relate linear and angular quantities, so omega is equal to v divided by r. And then on the right hand side here, because they stick together, the rotational inertia is going to be the combination of the ball and the stick, which is going to be mr squared plus, and this rod, we're going to use our chart, which I showed you earlier. And so it's going to be mr squared. Let's say the rod has a mass of mr squared divided by 3 times omega prime. And you'll notice that one of the r's cancels out on the left hand side, so we have mrv is equal to, and on the right hand side we have mr squared plus big mr squared, that's the big M is the rod's mass, divided by 3 times omega prime. So that's how you would set it up, and you would look for the unknown.